All right, today, so we're going to talk about probability, which is section 8.5. Now, this is going to be truncated down because we had to move scheduling around at the beginning of the semester for including Gini index. So there are going to be some things in this section. So if you're following along in your book, there are going to be some things that we are missing. So let's go ahead and get this thing started. So suppose that you have purchased stock in a company, and each day you note the closing price of the stock. The result each day is some real number X. Here would be the closing price of the stock in an unbounded interval from 0 to infinity. Now we know in situations like this that we're not going to have an infinite number or infinite dollar amount, but it could continue on. All right, another example. Suppose you track the time of several people running the 100-meter dash. The result of each runner is the real number X, so time in seconds. So just to give a reference, Usain Bolt holds the men's record. Again, this was just last fall when I checked these numbers. So Usain Bolt holds the men's record for 9.58 seconds, and Florence Griffith Jr. holds the women's record at 10.49 seconds. So, but in each case, there's a specific thing that's going on. So in both cases, the value of X is somewhat random. Okay? In fact, X can take on essentially any real number. So X can take on any real number or real value in some interval rather than just some integer value. So that's what we mean that it is somewhat random. Okay, so it's not just taking on values 1, 2, 3, 4. There's values in between. And because of this nature of X, this variable that we have here, we're going to give it a name. Okay, so X here is referred to then as a continuous random variable. We're going to talk more about that here in just a second. But to give you a contrast to that, okay, a discrete random variable is a variable that only assumes a number of separated values. And there's plenty of examples that you've seen in the real world that apply to this. A good example to really just start things off is a die. So again, an example is if you roll a die, your outcomes are very limited. So your outcomes would have been 1, 2, 3, 4, 5, and 6. So no values in between. So it only assumes these separate values that you're going to get there. Where in contrast, like going back to talk about Usain Bolt and those running the 100-meter dash, those could take on any value in between. Let's say we could start with Usain, have him be our bottom line. So if we wanted to say even 9 seconds and up, we could take on any single value in between there. And so that's what we mean, the difference between a continuous random variable and a discrete random variable. So again, discrete random variable is a variable that assumes a number of separated values, whereas continuous can take on any real value for that. So going back to our stock example. So if X is the closing price of stock, and we find out that 60% of the time the price is between $10 and $20, we could say that the probability that X and here I'm going to use a big X to represent that, is between 10 and 20, so $10 and $20, is 0.6. Or, mathematically speaking, so if we're going to use mathematical notation here, so I'm going to put an or here, and we'll do this in red, that P of 10 is less than or equal to X, which is less than or equal to 20, is equal to 0.6. So this is saying the probability that our variable X lies between 10 and 20 is 0.6. So it's the same thing, it's just we get to truncate it down. So this is why we like to use mathematical shorthand, because one, it saves a lot of time and it means exactly the same thing. All right. So with that, we can also visualize these things. So we can use a bar chart to display the probability that X lies in between selected ranges. And here I'm just making up some values just to give a visualization of what's going on. So we could say, okay, you're just giving us a line here. That this is 0, this is 10, 20, 30, 40, and 50. And inside of here is our probability. So I'm going to put those in green to give a little bit of a contrast. Here we'll say this is 0.05. So that means 5% lies between 0 and 10. Between 10 and 20, we just said is 0.6 or 60%. And 20 to 30, we're going to say 20 or 0.2. Here I'm going to say 0.10. And then here again 0.05. Okay? So if we started making finer groups, notice that it looks very similar to what we did with Riemann sums. And in fact, by matching this with a particular curve, again, be trying as best as possible to get a good representation here. So notice that this starts looking like a curve the more and more we make this a fine-tooth groupings. And in fact, this is what we would call a probability density histogram. So what the bar chart is, so probability to give it a very specific name. Now again, you don't need to know that for this section. If you were in a statistics course, yes, that would be very important. But here we're more interested in getting into the calculus-based information here. All right, so that's the cool thing, is we start seeing curves happen here. All right, well, every continuous random variable has a probability density function. Okay, so notice in order to get a curve, we need some expression, some equation in order to generate that. So this is where this idea of a function is coming from. So again, every continuous random variable x has a probability density function. And we'll just call him f. Okay. This means that the probability that x lies between A and B is found by integrating f from A to B. Notice here, this is talking about area here. Okay? So, we could really say then that P of A is less than or equal to x, which is less than or equal to b, is equal to the integral from A to B of f of x dx. And we can all do that. We've dealt with improper integrals. We've dealt with all these integrating techniques from Chapter 7. So these are pretty easy that we're going to get into. All right. So here's where our very strict definition is going to come into play. A probability density function and to help with writing this, I will call these PDFs. So probability density function, PDF, is where that's coming from. Okay, so is a function f defined on an interval a, b, and has the following properties. So we do have to be very strict on what we're doing here. All right, so the following properties are, here, f of x has to be greater than or equal to 0 for all x. Okay, so that makes sense. We're dealing with talking about the area underneath the curve. We're talking about probability. We're not going to deal with a negative probability. So it makes sense to have a positive function and or a 0 function. And the next piece here is, well, let's think about this. Probability, what is that out of? Well, you have a 0 to 1 chance of getting something done, right? Or a 1 to 1 or 0 to 100%. So that means that the area underneath the curve from A to B of f of x dx has to equal 1. Okay? 1 or 100%. So that means everything has to be out of 100%. Nothing more, nothing less. We are going to extend what the properties of A and B are. So we are going to allow A, B, or both to be infinity. The reason we say that is, one, we don't have to rewrite a new definition, and two, if we wanted to extend this out from negative infinity to infinity, we can, and we have the ability to do so using improper integrals techniques that we studied back in 7.8. Okay? All right. So let's look at our first example. So again, because of time and everything like that, take a second. I'm going to take a 5-second break from me talking, and I want you to work out this problem. So first, let f of x equal 2 over x squared on the interval from 1 to 2. I want you to first verify that f is a probability density function. So think about what you need to show. All right, the two properties that we just talked about. And then I want you to find the probability that our x variable lies between 1.5 and 2, and then find out when x is equal to 1.6. All right, so now that you've paused and tried out your problem, so let's walk through this one together. All right, so first of all, I want to verify. Okay, so part A is to verify that this is a PDF. Well, first of all, I need to look back at what these are, just to remind ourselves. All right, so part A says, for verifying, I need this to be positive or 0 for all values of x. Well, the nice thing is f of x, which is equal to 2 over x squared, we know x squared is going to be greater than or equal to 0 for all x. And in fact, we could go one step further with this one, since we're between 1 and 2. We can actually say that it's a strict inequality and say that x squared is greater than 0 for all x in the interval from 1 to 2. Okay? Well, if we know that the denominator is always positive, the numerator is always positive, then that means f of x is going to be greater than 0 for all x. Okay? So this is, and I'm going to put a little a here, saying this is part of our verifying. Little b here, we need to show the integral from a to b of f of x dx is equal to 1. Well, that's easy. We set up our integral from 1 to 2 of 2 over x squared dx. Again, to rewrite things, to make things a little bit simpler, I'm going to write this as 2x to the negative 2 dx. So we're using our power rule here. All right. So we add 1 to the exponent, so we're going to get x to the negative 1 divided by the new exponent, which is also negative 1. So in the end, we're going to get negative 2 over x, just as a rewrite. And now I'm going to evaluate that from 1 to 2. All right. When I do that, I'm going to get negative 2 divided by 2 minus a negative, so I'm going to get plus 2 over 1. So I'm going to get negative 1 plus 2, and this is equal to 1. So this is when I ask on a test or homework to verify that f is a PDF. This is what you have to do. You have to talk about the function, why it is positive or 0, and then show that the area underneath the curve is equal to 1. All right. Part B. I want to find, so now that we've verified, I want to find the probability that x lies between 1.5 and 2. So all I have to do for that part is p of 1.5 is less than or equal to x, which is less than or equal to 2. This is equal to the integral from 1.5 to 2 of 2 over x squared dx. Well, the nice thing is, let me write this to make it a little bit cleaner looking, is we've already found the antiderivative, so we get negative 2 over x, and evaluate it from 1.5 to 2. All right? So when I plug in 2, I'm going to get negative 1 out, and then I'm going to get plus 2 divided by 1.5. Well, that's negative 1 plus 2 over 3 halves, and then negative 1 plus 4 thirds. So this is equal to 1/3, or 0.33 repeating. Okay? So the probability that our x variable lies between 1.5 and 2 is 0.33333. All right? The next piece, p that x is equal to 1.6. So let's think about that for a second. We have an infinite number of values between 1 and 2. I know it sounds weird, but you got to think about that. We're dealing with real valued function here, so it can take on any single value in there. Okay? Think about this idea. What percentage, or what is the probability that you get exactly one value out of an infinite number of values? All right, well, let's think about this. Let's step through this piece by piece. So if I did with a regular die, so it has 6 faces, okay? The chances are rolling a 1 is a 1 in 6 chance, okay? Now let's assume that we're dealing with a 20-sided die, and I rolled a 1. The chances of rolling that is a 1 out of 20. Notice as I increase the number of sides, our chances become smaller and smaller and smaller. In fact, as we increase that to say that it has an infinite number of sides, which is an interesting idea at the least, then you'd have a 1 over as n approaches infinity. So think about that limit idea. What's going to happen? Well, the probability is going to go to 0. And another way to justify this is think about our integral. Our integral is from a to b. Well, that would be 1.6 to 1.6 of 2 over x squared dx. Well, that's equal to 0 because this is a 0 width interval. So there's a couple ways that we can justify this. So, just to write out what we just talked about, a continuous variable continuous random variable, has an infinite many possible sides or possible outcomes. So, the probability that a single outcome occurs is 0. So if this were to pop up on a test, you could just write the probability is equal to 0. Now, if I asked you to justify that, walk through the process. You could either show me, hey, I'm dealing with a zero width interval, so we know that no matter what the function is, provided that it's defined there, we know that this is going to equal 0. That's just basic properties of intervals. Or you could give a little bit further explanation and say, okay, if we start increasing the number of outcomes that occurs, the probability of getting exactly one to occur becomes smaller, 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 and as we increase that to infinity, we get 0 out. All right? So, now that we've walked through one together, I want you to go over this next example. So again, going to give a 5-second break here for you to pause the video and start working this out. Again, here we're going to let f of x equal 30x squared times 1 minus x, the quantity squared, on the interval from 0 to 1. Here, f of x is equal to 0 for all other values of x. Okay, so this is defined on all real numbers. I want first to verify f is a probability density function. So what are the two things that you need? And then find the probability that x is less than or equal to 1/3. All right? All right. So we need to verify. All right, so let's verify this thing. So let's talk about this. Well, f of x is equal to 30x squared, 1 minus x, the quantity squared. I know that x squared is always positive. Okay, or 0. And, in fact, because I have a squared term here, this is actually the same statement. That 1 minus x, though we can generate negative values, is always going to be squared, so therefore it's always positive, or 0. So, thus, f of x is greater than or equal to 0 on the interval from 0 to 1. And in fact, let's extend that out. Since we know f of x is equal to 0 for all values of x, for all other values of x, then this is true. That f of x is greater than or equal to 0 on the interval from negative infinity to infinity. Okay? So that's part A of our verification. Part B, okay? So part B says, okay, well now we need the integral from 0 to, or from negative infinity to infinity to be equal to 1. All right. Well, the nice thing is we actually have a piecewise defined function here. So on the interval, technically on the interval, we have 0 when x is between negative infinity and 0. It is now produced by 30x squared, 1 minus x, the quantity squared, when x lies exactly between 0 and 1. Oops, I wrote that backwards. And it's equal to 0 after that. Okay? So, Well, if we have a zero function, doesn't matter what the interval is, we can actually rewrite our integral. And here I'm going to show the rewrite. This is just simply equal to the integral from 0 to 1 of 30 x squared, 1 minus x, the quantity squared, dx. All right. So, moving some things around. I'm going to bring that 30 outside. FOIL the 1 minus x squared, and then distribute that x squared into there. So I'm going to get x squared minus 2x cubed plus x to the fourth dx. Well, this is going to equal 30, and now we go through our process of x cubed over 3 minus 1/2 x to the fourth plus 1/5 x to the fifth from 0 to 1. Nice thing here is we're dealing with a polynomial function here. So when I plug in 0, all of those values are going to go away. So I just need to evaluate this at 1. So in this case, I am going to get 30 times 1/30, which is equal to 1. So this is a PDF. So now I just need to deal with part B, which says find the probability that x is less than or equal to 1/3. Well, that's the integral from 0 to 1/3, because again, the reason I'm doing on a smaller interval here is because we know the function is piecewise defined and it's 0 everywhere else. So that means we only have to deal with the interval from 0 to 1/3. Okay, again, we want all values less than 1/3. Okay, so again, 30x squared, 1 minus x, the quantity squared dx. When we simplify this out, we get 30 times x cubed over 3 minus 1/2 x to the fourth plus 1/5 x to the fifth from 0 to 1/3. And when we plug in 1/3 into there, we will eventually get 17/81. Okay? All right. So that's where we're going to stop it for right now. This is essentially what you're going to be doing for the WebAssign and for the test. Very, very basic stuff. We are going to cover a little bit more in this section in the next video. I'm going to be dealing with the expected or mean value, and it's a very, very straightforward process, but I want to go through the proof of it so then that way you can see how we build finding this mean value of some continuous random variable.